We are going to find the maximum displacement of the beam shown below. The beam is steel and has the cross-sectional dimensions shown. So our first step is going to be establish the x-axis and draw the deflected shape. Just to give us ourselves an idea of where we're heading. So we expect this beam, right, no displacement at the pin and roller, and in between the load is pushing down. I quickly find my reactions. It's a nice symmetric beam, 1 kip per foot along the entire length. I will have 10 kips and 10 kips as my reactions. So I can quickly draw the shear and moment diagram, and I can see that my moment can be described by a single equation, which means I only need one x-coordinate. Without even drawing my moment diagram, I can tell if I'm going to need more than one x-coordinate if I have load changes. So anytime there's a load change, so a distributed load stops or starts, any type of point load, any concentrated moment, any reaction, we are going to need another x-coordinate or to make another cut to describe our moment diagram. We're going to need another slash cut on the structure. So for us, we have the same load across the entire length. As we see in our moment diagram, we can describe it with one equation. Right, and we hit our peak at 50 kip feet. Right, so we've done our first step, established our axes. We don't need to draw a shear and moment. It's just helpful to remind ourselves if we need to make more than one cut. You can easily tell that from the loads without going through the effort of shear and moment, though. Once we have our axes established, we can go ahead and express the internal moment as a function of those x-coordinates. In this case, we only have one, which we need to define. So if we don't establish it, we're going to have a hard time describing this moment diagram. I'm going to choose to start my one coordinate from left to right. I'm always going to want to start at a support or a free end. I don't want to just randomly start in the middle, because then I'm going to have an x-coordinate that could have negative values. This x-coordinate is talking about length. Our length should always be positive or non-existent. Right, so it should either be 0 or positive. So x is 0 here, x is 20 feet here, and where we expect the max displacement to occur, because this is a nice symmetric beam, we're expecting it to happen in the middle at x equals 10 feet, which would be right there. So we need to express this moment. The way we do that, right, the way we express a moment at any point, is by making a cut at an arbitrary spot. So I'm going to cut right here so that I can draw this half of the structure. So anything I see to the left in my green highlighted area, I need to draw in my free body diagram. If I want to draw the other side, right, I could draw this side and I would need to draw everything I see in that free body diagram. Doesn't matter which one you draw, I'll draw both just so we see them. If I were to draw the left side, so left hand side of my cut, I am going to see the pin with the distributed load, 1 kip per foot, the reaction of 10 kips, and the axial shear and moment I release. And I am drawing my moment based on positive sign convention. Right, so my moment is counterclockwise positive on this cut. Right, if I wanted to draw the right hand side instead, I would draw everything I see to the right of this cut, Right, make sure I draw equal and opposite and positive sign convention. See the distributed load. And the difference here is for my left-hand side drawing, this dimension is going to be x because I started my x here. If I were to draw this one, this length would not be x, it would be the entire length, 20 feet, minus x, right? Whatever is left over. So the reason I'm going to analyze the left-hand side of my free body diagram is because that's where I labeled my x-coordinate. That's where it's going to be easier to deal with, and I'll have less algebra to worry about making a mistake with. So again, either one will get you to the same answer. Choose whichever one is easier for you to deal with. So if we do that, take this one, move it over here, and I am going to take the moment about the cut. So we're always, for double integration, going to take the moment about the cut point. It makes our life nice and easy, gets rid of the axial and shear we released without having to find those values. I'm going to take my moment about the cut. I've got the m of x that I want to find. It's positive counterclockwise. I have minus 10 times x and plus 1 kip per foot, acting over x feet at a moment arm of x over 2. And my m of x is going to be 10x minus x squared over 2. Okay, and we can verify if we've drawn our moment diagram, we can verify that's true. If I look up here, here's where x is 0, here's where x is 10, here's where x is 20 feet. And if I plug those values into the formula, right, when x is 0, m is 0, that matches my diagram. When x is 10 feet, m is 10 times 10 minus 10 squared over 2, which is 50, matches my drawing. And when I plug in 20 feet, I have 200 minus 200, I get 0 again, which again matches my drawing. Alright, so you can always do a sanity check, look back at your moment diagram to make sure your moment equation makes sense. So once we have that, our next step is going to be to integrate our moment equation twice to get deflection. Right, we're trying to find the maximum displacement or deflection. Those words are interchangeable in this context. This is going to be the deflection equation, right? So not at a specific point, but everywhere along the length. So we have our formula, curvature, which is the second derivative of deflection, is equal to m over EI. I'm just going to move my EI over so it's on the left-hand side because it's constant. I don't need to be integrating that unless my EI is varying along the length. So I've got 10x squared over 2 minus x cubed over 6 plus c1, 10x cubed over 6 minus x to the 4th over 24 plus c1x plus c2. This is my deflection equation. The only problem is it has constants in it, and that's not helpful because I don't have an exact number for the deflection at every point. So we need to plug in our boundary conditions. You'll see me abbreviate it BCs at location x is 0. We have the pin, so our deflection at the pin is 0. The roller is at x is 20 feet, and the deflection there is also 0. So I'm going to plug it into my formula right here. I need to plug in these values. So EI times 0, because V is 0, when x is 0. 0 to the 4th over 24 plus C1 times 0 plus C2. This tells me C2 is 0. When I plug in 20 feet, my V is also 0, but I need to plug in 20 cubed, 20 to the 4th, 20, and I already know C2 is 0. This tells me C1 is minus 1000 over 3. I now could rewrite this equation as EIV is 10x cubed over 6 minus x to the 4th over 24 minus 1000 over 3 times x plus 0 because C2 is 0. So this is our deflection equation. You'll also see it called the equation of the elastic curve, meaning the line element describing our beam is the elastic curve. But this does not answer our question. Our question was asking, find the max. This is telling us deflection at every point, so we need to plug in the location of the max, and to do that we have to find the location. We have a pretty good idea, because of the symmetry, that it should be happening when x is 10, but we can verify that, or if we're not quite sure, remember that the maximum of a function in calculus occurs when your derivative is set equal to 0. So our max displacement occurs when the derivative is 0. Right, this is only true for our simply supported beams, or basically beams that are not cantilevers. If we have a cantilever, this statement is not true. Alright, we'll talk about that on the next example. So all we have to do here is set our dv dx, which is our theta equation, and set it equal to 0. So 10x squared over 2 minus x cubed over 6 minus 1000 over 3 is equal to 0, and solve for x, and we should get cubic roots, one of which will be 10 feet, and it'll be the only one that makes sense, and we'll talk about how those make sense on the third example. So we do see that this is a solution to the derivative being equal to 0. Again, this is not our answer either. This is the location of the max displacement. We need to plug in to the v of x equation to actually find v max. Alright, so that is our last step. The max displacement occurs at x is 10 feet. So we're going to write that. So v max is when x is 10 feet. I'm going to move my EI over, and I'm going to plug in 10 feet. So 10 times 10 cubed over 6 minus 10 to the 4th over 24 minus 1000 over 3 times 10. So I've got a couple issues here. I need to find my EI, and I also need to make sure my units are good. So let's deal with our EI first, and then we'll deal with our units. So coming back up here, this tells me the beam is steel, which means E is 29,000 KSI, Gibbs per square inch. Gibbs per square inch. I need to calculate my moment of inertia, because I'm just given the cross-section. So these values are given based on what would be given in the steel manual describing all our shapes. D is the total depth of the section. So this one's 21 inches, so it's nearly 2 feet deep. B sub F is the width of our flange. Remember, this is a flange, and this is the web. BF is the width of the flange, TF is the thickness of the flange, and TW is the thickness of the web. So we can approach this a couple ways. We could do parallel axis theorem, calculate just the moment of inertia of each of these pieces. Right, so I could break it into this rectangle, and this rectangle, and then this one in the middle, so 1, 2, 3, and use parallel axis theorem. That's going to be a bit of a mess. So instead what I'm going to do is I am going to say I know the moment of inertia for this full rectangle. That is going to be 1/12 base times height, so BF times d cubed. So remember, for our rectangles, moment of inertia is 1/12 base times height cubed. 1/12 BH cubed. That is the moment of inertia if this was just a full rectangle, but I have these little rectangles that are cut out, but very conveniently the centroid of these little rectangles is the same as the centroid of my overall rectangle and the same as the centroid of this eye shape, so I don't have to use parallel axis theorem. I can just subtract out minus 1/12, and I need the base of this, which is going to be BF minus TW over 2. BF minus TW over 2. And the height of this is going to be D minus 2TF. D minus 2TF. And that quantity squared, or sorry, that quantity cubed. Minus another one of those. Cubed. And I can put that all together, and I will get my moment of inertia for this eye shape is 1143 inches to the fourth. So I have my E, I have my I, and now we notice these are in kips per inch squared times inches to the fourth. So that's going to be inches squared. So this denominator is kip inches squared. Now my mess of my deflection equation, let's go back and think about this. So the units on our moment are kip feet. When we integrate, it's just a fancy way of calculating area under the curve, so we're calculating area under the moment diagram. The units on the moment diagram are kip feet, and the units on the length of that diagram are feet, so we're just multiplying by feet. So kip feet squared, and we integrate one more time, and we get kip feet cubed. So we have 1 over kip inches squared, and then in the brackets, the units over here are kip feet cubed. So our kips cancel, and the units we want over here, probably inches. If we're talking about our civil structures deflecting in feet, we have bigger problems on our hands. So we're going to want to convert this to inches. So right now, here I have feet cubed over inches squared. If I convert this, so times 12 cubed, right, that'll be my inches cubed, would give me my 1 foot cubed. Those cancel, and we are left with inches. So I need right here in the numerator a 12 cubed. Alright, I don't ever have to think about this again. Anytime I'm dealing with imperial units and I'm talking about a deflection using double integration, I should be seeing 12 cubed in my numerator when I simplify my answer. Alright, so let's actually plug and chug that out. Alright, now that I know that this is 29,000 and 1143 times that same mess in brackets, and I'm going to get Vmax is a negative 0.11 inches. We said before, sign convention, negative means downward, so this is 0.11 inches down at its maximum. Alright, so we've answered the question where you're talking about the deflection of this beam right here. At x is 10 feet, we are going to see a deflection of 0.11 inches. Alright, if we want to know the deflection at any other location, we can plug in that x location, and it will tell us the deflection there.